Hello. Let's see. Okay. Oops. Okay, you should hear me by now and should see the desktop. Oh, let me get the chat up. Does everything seem okay? Do you hear me? Do you see
Yep.
the desktop? Okay. All right. Okay. So what we're going to do today is continue to talk about matrices and transformations. Okay. So let me download these two zip files. Okay. Okay. Um, Now remember, what we're doing is actually. I also want to, for comparison purposes, I'm going to download Renderer 6 so that so we can look at some examples of what's changed. Let's see. Now, like if we look at this, if we run this, we can make the cube move around. Yeah, we can make the cube move. Okay, and the way we were making the cube move was by oops, the the key handler is in this file abstract client. Okay, and I'm trying to remember. Okay, see, if you use any of these keys, I call this function called do transformation. Okay, and do transformation actually does the moving. Okay, the do transformation checks which key it is. Okay, and then it either calls scale, a model called scale, or this move model. We've used this move model function a lot, and move model just iterated through all the vertices, and here's the final thing: it changed each vertex. Okay. Okay. So it would change the vertices because it would have to go through and modify each vertex. So it would add to the components of the vertex. And this is what we're trying to avoid doing. We don't want to have to write code that reaches into an object and causes the object and moves all the vertices in the object. Okay. So we want to do something more that's easier to work with. Remember, in this, the formulas for rotating this, see, this was real easy. This is just moving it left and right or up and down. See, delta X, delta Y, delta Z. So up and down, left and right, forwards and backwards. So that's really easy. And it wasn't hard to scale it, which was just multiplying each component by a number. Translating was adding a number to each component. Scaling is just multiplying each number by component. But rotating is a much more complex operation where what you do to X depends, you have to use a fairly complicated formula on all of X, Y, and Z simultaneously. Okay, so we want to stop doing this, iterating through the vertex list and mutating every vertex. Okay, so what we're going to do now is we're going to use matrices to actually move vertices. Okay, so we saw from pictures we looked at, the idea is that this, if you give me, this is only 2D, but the idea is the same with 3D. If you give me a vertex and I multiply it by this matrix, I get a new vertex is the rotated one. That matrix that idea, this step here, which see it gives you these formulas here. Like these are the formulas I say that actually are the rotation formulas. Okay, it's here's the actual rotation formulas here. Okay, so if actually a minute ago we were looking at render 6. If I did want to put a rotation in here, if I wanted to rotate model, if I did want to put rotate model, it isn't really, I mean, I said it's more complicated, but it would be replacing those formulas with these formulas, okay? But that would only rotate around the z-axis. Then you'd need need a rotation around the x-axis and rotation around the y-axis. So you'd have to have 3 sets of these formulas. So you would need rotate around the x-axis, rotate around the y-axis, rotate around the z-axis. That's part of what I meant by it gets kind of complicated. Okay? But where you would update these vertices, the components of the vertex, you'd use this formula here. Okay, but instead of typing in those formulas and iterating through the vertex list and making those changes to every vertex, what we're going to do is we're going to see that we're actually not even going to do this matrix multiplication ourselves. Only the renderer will actually do this multiplication. We're just going to say that we want to use a matrix, and we'll leave it up to the renderer to actually do these formulas. And that's actually the key idea, is that what we're moving to is something called a declarative model. Instead of actually doing the transformation, we will just say, here is the matrix that does the transformation. And essentially what we're doing is we're declaring what the transformation is, but not actually doing it, and then leaving it up to somebody else to do the transformation. Okay, that's the kind of abstract way of thinking about it. It's a fundamental idea of computer science to declare something without actually doing it, to just say, this is what I want done, and then leave it up to somebody else to do it. Here, we're doing what we want done. We're actually moving the vertex. Here, we're scaling the vertex. If I wanted to, I could put I could put a rotate model in here that used these formulas to rotate a vertex, and then I could rotate a model. And that'd be actually doing it right here. But what we're going to do is we're going to actually say that there's going to be a matrix attached to the model, and that matrix is going to be saying, oh, here's how I want the model to be moved when you get around to moving it. So you're essentially declaring what to do, not how to do it. So the matrix is a declarative thing. It says what to do. The formulas are how to do it. Okay. So this matrix, it declares these formulas, but it doesn't. But the matrix by itself doesn't do those. It's only when you actually do the multiplication. If you just attach the matrix to the model, that's what we're going to do. We're going to attach the matrix to the model, and then we essentially said, by the way, somebody needs to apply this matrix to every vertex in the model and move the model. Okay, but that won't be in our code. That will be actually, what will be in our code is attach the matrix to the model, and then what will be in the renderer will be essentially the equivalent of this that applies the matrix to the model. Okay, so let's see what we mean by how that works. Okay, if you look at the README for render 7, it points out that the scene data structure is going to be updated. Instead of scene be a list of model, okay, let me build a Java doc. Okay. That's the Java doc for render 6. We build the Java doc for render 7. And here's what a scene looks like, okay, in render 6, okay? And then in render 7, compare, there's going to be a difference in how the scene looks. Okay, here's what the scene looks like now. Okay, so this is the older render, and this is the new one. Okay, in the old render, a scene is a list of models. And so there's the list of models, and each model has a vertex list, a color list, and a line segment list. Now, right now, we're only interested in the vertex list. We're interested in keeping track of where the vertices are in the model. Okay, and if you wanted to move that model, you went in here and changed X, changed Y, changed Z in every vertex, changed X, changed Y, changed Z. That's how we moved the model. We would go through the list of models, and for every model, we go through the list of vertices and change every vertex. Okay, now the new render is more sophisticated. What it does is, instead of the scene being a list of models, the scene is a list of positions. Okay, so we think of space as being places where you can put something. So a position is a place in space where you have a lamp or a table or a football. Okay, and each position is a matrix that declares where the model sits. So this is why I say that you associate a matrix to each model. Okay, so this is the declarative part. Okay, now over here, if I wanted a model, say, with 3 chairs, suppose this was chair 1, chair 2, and chair 3, okay? I would have, now the chairs would be identical chairs. They would actually essentially hold the same vertices, but I'd have to go down in here and move all the vertices of one chair to position it in one place, then go down here and move all the vertices of the other chair to position it in another place, and then go down here and move all the vertices in that chair to put it in a different place. Okay, so if the chair was 1,000 vertices, I'd have to move the 1,000 vertices in here, the 1,000 vertices in here, and the 1,000 vertices in here. Over here, what I'm going to do is I'm going to have a chair. So that's the chair, and the chair. And then I don't reach inside here and do anything to the vertices of the chair. I go here and say, here's the matrix that says where this chair sits in space. Here's a matrix that says where this chair sits in space. Here's a matrix that says where this chair sits in space. If I want to move this chair, I'd have to reach inside of the model and move all 1,000 vertices. Okay. If I want to move this chair, I just reach inside of that matrix and make a change to the matrix. And the matrix is going to be, we'll see 16 numbers. And it doesn't matter how big this model is. This model could be millions of vertices. If I want to move it, I just change that matrix. Okay. Now that's my point of view. The renderer will have to apply that matrix to the model to actually get the vertices in the model to be in the right place. But that's done by the renderer. This is the declarative aspect. We declare here that this matrix should be used to move this model to a place in front of the camera. And we only declare that here It's the renderer's job to actually do the work. Over here, we were doing essentially we were doing all the work ourselves. If we wanted this chair to move, we had to go into the list of vertices of the chair and update every vertex in the chair to be in the right place. That put a lot of burden on us, and is it's actually very inefficient. We end up having to move the model. We'll see that it would cause us to have to move the model way more often than we would need to. Okay, over here, it's going to be much more efficient to move the model. Besides being easier to program and easier to think about. Once you're used to this, it's easier to think about. It's also way more efficient. It's going to be easier to think about and easier to use than this one was, but it takes a little bit of getting used to. Okay. Now, yeah, over here, like I said, we could have rotated the chair if we wanted to write that rotate model method that used the formulas, but we'd have to write a rotate around the x-axis, a rotate around the z-axis, a rotate around the y-axis, and it would just be, I didn't want to do it because it would be pointless. It's just the wrong way to do things. It's doable, but it's just the wrong way to do things. Over here, we're going to have a matrix for rotate around the x-axis, and a matrix for rotate around the y-axis, and a matrix for rotate around the z-axis. We do need 3 different matrices. Okay, we need one for rotate around x, one for rotate around y, one for rotate around z. And if you want to do a more complicated rotation, you multiply those matrices together. So if you like want to tilt the Earth on its axis, well, that's not rotating exactly on the x, y, or z axis. So then you have to use a combination of, you have to multiply here. You'd have to multiply here a couple of matrices. So this matrix would actually be a product of couple rotation matrices. Okay. All right. So this is our new scene. Now, the model looks exactly the same here and here. Model doesn't change. Okay. The structure of a model is exactly the same. The big difference is a scene is a list of places in space, and at each place in space, at each place, the matrix is what determines it's a place in space, where it is, and then the model says what to put there. Okay. Now, the example I just gave you, let me show you why this is kind of good. I said, what if I have 3 chairs? 1, 2, 3 chairs. Okay. I don't actually even have to make 3 copies of the model. There's an example down here. Oh, I'm sorry. It's not in this file. It's in the README. It hasn't been moved to that file yet. Here's an example of a scene that would have 1, 2, 3 chairs. So there's 3 positions, a position for that chair. So it's got the matrix and then where the chair, then a position for this chair, putting it someplace, and a position for this chair, putting it someplace. But this chair, and this chair are the same chair. So you can actually create what's a graph like this. See, this is a tree, but now our scene is actually what we call a scene graph. It's no longer actually a scene tree anymore. It's going to be a scene graph like this. I can have these positions share that chair. So that position says, use this matrix. Now, notice that this is the declarative model. It's actually not actually doing anything yet. It's just saying, I have a position, this is where it is, and it holds a chair. I have another position, it's in a different place, but it holds essentially, it holds a copy of the same chair. And I have a position in a different place, and it holds another copy of this chair. The renderer will turn this back into this. The renderer will end up having, since this chair is full, say this chair's got 1,000 vertices in it, those 1,000 vertices have to be in one place. So what that means is the renderer will have to apply this matrix to this chair and make a copy of the chair and put it there. They'll have to apply this matrix to the chair and make a copy of the chair holding the updated vertices. They'll apply this matrix to this chair, but make a copy of the chair and put it there. So the renderer will turn this graph back into this tree. Okay, but then the matrices will be gone. Then it'll just be it'll actually be back to this thing here. It'll just be a chair that's been moved to where it belongs, a chair that's been moved to where it belongs and a chair that's been moved to where it belongs. So the render will take this thing here and it'll use the matrices to update one copy of the chair and put it there. And the matrix, then this is ready to be drawn because the chair will be in its right location. At that point, after this matrix has been applied, to everything in this chair, and a copy of the chair is put there. From then on, the matrix is ignored. It's not used anymore. Then this matrix is applied to a copy of this chair, and this is the updated chair with the vertices updated, just like we did over here. But now this matrix is going to get ignored. It's done its job. Okay, and then this matrix will be used to mutate a third copy of the chair model, and that'll be put under that position, and this matrix will not be used anymore. So that's what the render is going to do. The render is going to be able to take something like this, and here we're saying that we have, yeah, the render is going to say that our scene graph declares that we've got 3 chairs in 3 different places, but it's only got 1 chair model. You can't draw 1 chair in 3 places. The vertices in this chair are either over here or over there. So you have to make 3, the render will make 3 copies of the chair, apply that matrix to 1 copy, then put that new model in that position. Then it'll take that matrix, apply to that chair, a copy of that chair model, and put it there in the tree, and do the same over here. And after that, the matrices get ignored. Okay. I was just thinking something. What's a big advantage to this? I mean, think of a game where you have a forest. Think of a game where there's 27 trees in a forest. If you look carefully, you might notice that the trees, and a lot of times the trees will actually be identical trees because they're doing something like this. They'll have 1 tree model, and they'll have it with 27 different matrices, and the matrices can be positioned, they can be scaling so the tree can grow a little bit. One tree can grow a little bit, one tree can shrink a little bit. They'll be put in different places. And what's the advantage of that? You only have to, instead of sending 27 tree models to the graphics card, you send only 1 tree model to the graphics card. In this case, only 1 chair model is sent to the graphics card. If it's an elaborate chair model, it could have thousands, even millions of vertices. It's very advantageous to only send 1 chair model to the graphics card. Okay. Now the graphics card still has to make a bunch of copies of it. The graphics card will, our render is replacing the graphics card. It'll make copies of that model, but the communication cost in a real render is pretty high. So sending a model to the GPU is a pretty important thing. Okay. You only want to send the model to the GPU once and then let the GPU make the copies it needs. In our case, we don't send anything. We just make the copies in our own render. Our render will make a copy of this chair, make a copy here, and make a copy here. So it has to go through the process of making copies. We don't have a communication step in our render because we're not sending a copy of the chair or the tree from the CPU's memory to the GPU's memory. But in a real GPU, that's what you have to do. This chair is sitting in the CPU's memory and has to be sent to the GPU's memory. This thing, one of the big advantages of this is that chair is only sent once. And then the GPU will make the copies. But the GPU is real fast at making the copies. Okay. And it also just, once you get used to it, it makes it very easy to think about designing things. It's a lot easier to just think of there being this 1 model here and it's placed in 3 different places. And then if you don't want these to be identical chairs, then you go back up here, and then if you have 3 chairs but they're not identical chairs, then you always can use this structure here. You can give each position its own chair, or you could have 2 chairs shared and a 3rd chair be different. Okay, you have a lot of leeway here. You don't have to have it as a tree. You can have it as a graph. The renderer will unravel this graph into a tree because there has to be, that chair has to hold different vertices than that chair. When it actually gets drawn, that chair has to be in one place and that chair has to be another place. So you have to actually plot these points in one place in the frame buffer, and these have to be plotted in a different place in the frame buffer. So there have to be different vertices so that these vertices can appear one place in the frame buffer and these vertices can appear a different place in the frame buffer. But notice that in the declarative model down here, there just can be one chair model because it's not, this is declarative. It's just saying what to do, not how to do it. So it's just saying there's going to be 3 copies of a chair, and the one copy is placed in where this matrix says to place it, one's placed where this matrix says to place it, and one is placed where this matrix says to place it. And the only thing this says is that the chairs are identical to each other. Yeah, so there's 3 chairs that are identical. If you look up here, it says 3 chairs. They may be identical, they may not be identical. These models may actually be copies of each other shifted around. Or, well, they may actually be the exact same model, but you could put 3 copies right here. So you could just have this model be an exact copy of this model, which is an exact copy of this model. There wouldn't really any good reason to do that. If they were exact copies, there wouldn't be any advantage to drawing it this way, to having that, not sharing the reference to that chair. Okay, there wouldn't, if this and this were the exact same chair, there'd be no good reason to have it 3 times in memory when you could have it just once in memory. But if you did want this chair to be different than that chair, then you would need 2 different models. Okay, so that's our declarative way of doing things. We attach a matrix to a chair. We attach a matrix to a model. We think of that as a position. Where in space, the matrix says where in space that position is, and the model says what is located there. Okay. All right. Now let's look at how this would look in code. Let me do a simple example. Um, let's just write an example. Okay. Now I can try. I don't have a. I should have a template for what a simple example looks like. Okay. So here's, I need to import this kind of, I want to import all these. So even in a simple example, I'm pretty much always going to import the same thing. So I want to import the render files. Okay. Actually, I don't need that one. Okay. Okay. And then I'm going to need a declaration of a main method. Okay. Okay. Now, if we just do a simple example, we're going to create a scene and create a camera. Well, we'll use the default camera. This one used this one was using an orthographic camera. We'll just use we'll use the default perspective camera. Okay, and we need a model. So let me create a square model. Just create a model of a square. So a square size 1. Well, just the default square. Okay, so our model will just be a square. Okay, okay. Now we've got to give the square some color. So give it a color. I'll change it to red. And now here's what's going to be. We're going to create a position. We want to add the model to the scene. Now, before we would just add the model to the scene, but now what we add to the scene is a position that holds that model. Now, remember, a position held two things, a matrix and a model. If you look at the code for the position object, when you give it a model, it makes that the model in the position, and it makes the matrix the identity matrix. Okay, so that puts this model sitting at the origin. It doesn't move it. So right now that model is sitting at the origin. Now that creates the position. Then we need to add it to the position list. We needed to add it to the scene's position list. We add that position. Okay. All right. Now, then we need to create a frame buffer. Okay. Create a small frame buffer. And then let's just render and render it into a file name. Okay. And let's see what I do. Oh, I copy and pasted. I actually called the model, not M. So that should be model, and that should be model. Okay. So it's a real simple. Okay. So I've got a very simple scene graph right now. Okay. If the scene graph is just a scene. Now, one of the things that we'll do when we're doing is draw a picture of the scene graph of that we use. Like right now, what we have is we have a scene with a single position under it. And that single position has a matrix and a model. So our scene, what we call the scene graph, looks like this now. Real simple. And the model is a square. Okay. And the matrix is right now the identity matrix. Okay. So that's our scene graph right now. Right now, the matrix is the identity matrix and it's square. And if we compile that and then run it, okay. Now, I forgot something. Okay. Does anybody remember what I forgot? Notice I didn't get it. See, now I have to debug it. There's nothing there. Does anybody remember what? Does anybody see what I forgot to do? Let's open the square class. Okay, square class. It's just, the default constructor is a square size 1. Okay. Here's the vertices, the 4 vertices. Notice it's by default in the z equals 0 plane. Okay. See, it's by default in it, but that's a problem. Why?
You need to push it back.
Yeah, you have to put, right now, it needs to be in front of the camera, right?
Right.
And right now it's what?
It's inside the camera.
Yeah, or on top of the camera, however you want to think it. It's in the plane of the camera. It's not in front of the camera. So I need to push it back. Now that's a transformation. So what I need to do is I need to use a transformation. So I'll do that with this matrix. Instead of this being the identity matrix, I'm going to make this a translation, say by -1. What I want to do is I want to replace the matrix with a translation by -1. Okay. Now let's see how we would do that. Okay. Let's look at the code for the position object. Okay. A position object has a model and a matrix. See, it holds a model and a matrix. The default constructor gives you no model and the identity matrix. Okay. If you use this constructor, that puts that model in the position and gives you the identity matrix. Okay. And notice that there is no constructor that takes a matrix. Okay. So the idea is that you update the matrix after you create the position object. So there is no constructor. There could be. I just didn't define a constructor that took a matrix. It didn't seem to be really useful. So after you create a position, then you need to update the matrix. Okay. Now you can update the model by calling set model. You can set the matrix to the identity. Okay. But notice that only sets the matrix to the identity matrix. So how else would you set the matrix? Well, these things are public, so you can just go ahead and multiply matrices with that matrix. When you build the model, it holds the identity matrix. If you want to change it, you can just go ahead and do a matrix multiplication between the identity matrix and some other matrix. Okay. So what that means is we'll do the following. Okay. After we've created the scene, okay, after we created the position in the scene, I can just do position dot matrix. Well, remember we talked the other day about the code for multiplying matrices. Like what is the what way are we going to how should we multiply matrices? Okay. What I want to do right now is something like this. I really want to do something like M1. Well, let's see, say M2 equals M1 times M0. I want to take the product of two matrices and create a new matrix. Right, like right now, this one's the identity matrix, and I want this to be a translation matrix. So I want this matrix to be the product of the identity and the translation, which is the same thing as just saying I want this thing to be the translation matrix. Okay, so now we have to have a way of writing that in Java. Okay, so we have to have the way we write that in Java is if M1 is a matrix, we say times M0. Okay, so M1 times M0 will be that matrix times that matrix. Now the times will return a reference to a new matrix. This will take that matrix object and that matrix object and build a third matrix object, and then we can store that in M2. So M2 will hold a reference to the third matrix object. Okay, so that's one way to do this. Okay, I mean there's other ways to do it. If you could also do something like this. I write it. I've used M multiply to mean M for mutate. This would take this matrix and use it to update this matrix. So that would mutate M1. Okay. Now, some renderers are written this way. When you multiply a matrix times another matrix, this matrix is used to mutate this matrix. Then you don't even need this one. if you want, you can, this just becomes an alias now. M2 just becomes an alias to M1, okay? So you don't even really need M2. The render that we're using is written this way, okay? It's going to say a matrix times a matrix returns a third matrix, so we can make that a reference to that, okay? Now over here, what we can do is we can say that matrix is the position matrix I want to update the position matrix. So actually what I'm really doing, if I go over here, I'm really going to now say I want this to be M1 equals M1 times M0. Then this would be updating M1. Okay. So then these would be 3 different ways of updating M1. But this says take the product of M1 and M2 and call the result M1. This says take the product of M1 with M0. That creates a third matrix. Just make M1 a reference to that new matrix. And then the old version of M1 gets garbage collected. So this would garbage collect the old M1. This one mutates M1. Okay. In the grand, this is really the difference between this and this is a big deal. People who write renders argue a lot about whether it should be this way or this way. Okay. If you think about that, here's what this is doing. It's taking a reference to one matrix and a reference to another matrix. It's instantiating a third matrix and then garbage collecting one of the matrices. Okay, so we start off with 2 matrices, M0 and M1, and we want the result of the product to be M1. So we start with 2 matrices, we build a third matrix, and we garbage collect 1 matrix. Now, on your hand, this one takes that matrix and uses it to just update that matrix. No garbage collection, no creating. Okay, so this one creates a new matrix, garbage collects old. Okay, so creates new matrix, garbage collects old M1. This one just mutates M1. So you'd expect this to be a lot faster because it's not doing the mutation. It's not doing creating a new object. So it creates a new matrix object and garbage collects old M1 object. So you have to create a new object and garbage collect an old object. Okay, now that's a lot of work. And now why this is way more work than this. Okay, this is just going to update the numbers in that matrix. Okay, so this will just however many, like there's going to be 16 numbers in this matrix. So this updates the 16 numbers in that matrix. This one creates a whole new matrix to hold the updated numbers, then has to garbage collect the old matrix. Okay, why would people use this at all if this is going to be way faster? And it's got to do with the way modern programming, ideas of modern programming, mutating things makes it harder to reason about programs. It might make the program faster, but it tends to make code more brittle and harder to understand and more error prone. And it's a big battle over what's more important, speed or code that's easy to read and understand and modify. Sometimes speed is super important. So sometimes you want this because speed really is the only thing that matters to you. If your code is hard to maintain, that's okay. You just work harder at maintaining it. Other times you want the code to just be easier to maintain. Okay. And what you do in this case is you just say, let's write a really good garbage collector that, and let's write a really fast creation algorithm that mitigates this to be almost as fast as this. The Java virtual machine tries very hard to make this come as close as possible to this. And actually, they're pretty good at it. You do pay a penalty for doing this, but it keeps getting less and less as time goes on, and the Java virtual machine and the .NET virtual machine, as they get better and better, they're they're narrowing this, the penalty you pay for here compared to this. It's still a pretty stiff penalty. It's not, they're not within a few percent of this. This is not going to be within a few percent of this. It might be 50% as fast as this. But 10 or 15 years ago, this would be 2 or 3 times slower than this. So it used to be this was many times slower than this. Now, maybe it's 50% slower, which is a way better than it used to be. But the code can be much easier to read. Okay. Now the render that we're using is actually does things this way. It doesn't mutate the matrices. Okay. So we would say matrix, the matrix in the position is going to be a matrix in the position times, we want a translation matrix here. So right now here we want a translation matrix. So we have to create a new matrix. Over here I wrote the formulas as if the matrices already exist. So somebody had already created this matrix and someone had already created this matrix. Somebody had already created this and somebody had already created this. Okay, here I'm going to create the translation matrix. Now, if we go over to the matrix class, the matrix class has got a bunch of, if you want to build a matrix, you usually call new, okay? But that's not how this is designed. There's a problem with new, okay? Suppose I say here, I want a new translation by, say, 0 in the x direction, 0 in the y direction, -1 in the z direction. I want to push things back. This doesn't work very well, okay? Now let me show you what I mean by it doesn't work very well. Suppose now I want to rotate the model. So after I pushed it, now I could update the matrix with a rotation. So, and I'll rotate around, say, the for staring down, we'll rotate around the z-axis by, say, 45 degrees. Okay. So this would say, take this matrix. The matrix is the identity matrix. Oops. So it starts out as the identity matrix, then it's being multiplied times a translation, then multiplied by times a rotation. That's what this code would do. First, it would take the original identity matrix, multiply it on the right by a translation. So that would do this. So that would be, in the order of operations, would be doing it like that. And then that then that matrix would become this matrix. And then you would say, okay, now multiply it by a rotation matrix. Okay. This is really not good, because here's the trouble. This means I have a translation class. This means I have a rotation class. Then if I wanted to scale the model, I'd have to have like if I wanted to then do times a scaling. So suppose I was actually doing a translation, rotation, and a scaling. I could then do something like this. And I could scale the model, say, 75% smaller. Okay. That would mean I have to have a translation class, a rotation class, and a scaling class. And they would have to be subclasses of matrix. And this becomes a nightmare to write. And it's only because I want constructors that are essentially easy to read. I want a constructor that says I want a new translation, a new rotation, a new scaling. And then I'd have to have all these subclasses of matrix. This is actually this is another big problem with Java and object-oriented programming languages. Constructors aren't as great as you're led to believe when you take freshman programming classes. Okay, the constructor can only construct matrix objects. If you want to construct a matrix that is a translation, you have to overload the constructor name. So then you have to do something like this. you could do this and say, okay, if the constructor has 3 parameters, that means it's a translation. But you have to just kind of say that. It doesn't say it here, but you'd have to say, okay, if the constructor has 3 arguments, that's the translation constructor. And then if the constructor has 1 argument, that's the scale constructor. But then I can't, what do I do about rotation? Rotation has to have, first of all, I have to say what axis to do it on. So you could have an enum, for example, that says, you'd have something like Z. You have to do things like put enums to say, I want a matrix where the constructor takes an enumeration that says, I want a rotation. This means rotation around the Z axis. So anybody see what this is building up to when you do something like this? A lot of libraries do it this way. They start overloading their constructors and giving them enums. But what's wrong with this?
It's too verbose.
Pardon me?
There's too much type.
No, you're going to have the enums are the enum is verbose. The enum really does feel very verbose, but otherwise, no. You're still saying, you have to create a new object. You need to create a new, Here I'm just using the word matrix instead of translation. Here I'm using the word matrix instead of rotation. I have to type about the same amount. There is a little bit of verbosity in the enum. What else is wrong with this?
Maybe it's not as easy to read and determine which is what.
Yeah, it's very hard to read. Which matrix am I building here? Well, 1 parameter means what? Which matrix am I building here? Well, 2 parameters with an enum means what? What matrix am I building here? It becomes very hard to figure these things out. Okay, so now one possibility is you do a lot of you have subclasses. Okay, now notice the choices. You could have all these subclasses, or you could have all these. You could have all these subclasses or all these overloaded constructors. All the subclasses is way too much coding, and all the overloaded constructors is way too hard to read. Somebody invented a really clever idea at one point. Okay, factory methods. You may have heard that phrase. Turns out that factory methods are the right way to do this. Okay, so here's what we're going to do. Instead of saying new with a constructor, we're going to call a static method named translate. And since it's a method, I'll lowercase the name now. What I'm going to do is I'm going to fill the matrix class with static methods. The method builds an object and returns it. And we call these factory methods, static methods that build objects. If you look at a lot of modern code, you'll see that a lot of people have completely deprecated constructors. They don't use them anymore. They've replaced them almost entirely with factory methods, because factory methods end up giving you fairly clean code. Yeah, I could say I want a translation matrix, a rotation matrix, a scaling matrix. Okay.
Wait, isn't this one of the design patterns done by the Gang of Four? You know what I'm talking about?
It is. I don't know if they really invented. I think it predates them. I think the factory pattern really kind of predated them. But I'm not sure if the factory pattern is one of theirs or not. Oh yeah, it is. Yeah, it is one of the Gang of Four patterns. Okay, so it goes, but it predates them. Okay, So factory methods. Okay. Now in the case of Java, okay, let's go over here. Here's what they look like. See, there's a factory method to build me an identity matrix. Notice it's a static method. And see, in the comment, I say this is a static factory method. What it does is the identity method returns a matrix. So, and it's going to return, I mean, that's the scaling matrix with 1, 1, 1 is just an identity matrix. So it's a trick that the identity matrix is just a scaling matrix with 1, 1, 1, scale by 1 in each direction. Here's the translation factory method. The static translate method returns a matrix. And see, I wrote a generic build method that will build the matrix. And so I'm returning a new matrix. So build is a generic factory method. So what I did was I wrote a generic factory method, and then each factory method calls build with the right column vectors. A matrix is 4 column vectors. If you think about matrices in linear algebra, one way to think, well, we'll see that there's 4 columns in a matrix. Normally, you would think for R3, there'd be 3 columns in a matrix. We haven't explained yet why we need 4, but it turns out that we need 4 column vectors in a matrix, not 3. Okay, so I built a generic factory method called build. Okay, so here's the kind of generic factory method that takes 4 column vectors and builds you a matrix out of the 4 column vectors. Okay. And it's mostly used as a helper method for the other factory methods. Okay, so it takes 4 column vectors and builds a new matrix. Okay, and then you can use the build method to build new factory methods. So there's translate, there's scale. Now that's scale with 1 parameter. So now here I can now I can do nice overloading. I can combine factory methods with overloading. Scale with 1 parameter scales by the same amount in all directions. But if I want to scale by 1 factor in the x direction, a different factor in the y direction, and a different factor in the z direction, so if I want to take a circle and squish it into an ellipse, then I use this scaling. So this scaling would take a sphere and squish it into a football, or take a circle and squish it into an ellipse. This thing would just take a circle and make it grow or shrink. Okay, so this is a uniform scaling. This is a non-uniform scaling. Okay, so I can still use overloading. Okay, so but then I can overload in a pretty convenient way. Then rotate by x, and there's the angle to rotate by. Rotate by y, there's the angle to rotate by. Rotate by z, there's the angle to rotate by. But notice that these all call a generic rotation factory method that take what axis to rotate on. So rotate on x means you're going to rotate on the axis 1, 0, 0. See, that vector points in the x direction. Rotate by y takes the amount of, you call the generic rotate factory method. It builds a rotation of theta around the axis 0, 1, 0, which points in the y direction. Rotate z, you're going to rotate around the z-axis. That's to rotate around the vector 0, 0, 1. 0, 0, 1 points in the z direction. And then here's the generic rotate. It's really a mess. This rotates around any axis, x, y, z. This is a real famous formula. This is something you just you go to the Wikipedia page, look up the rotation formula, and then you just sort of copy and paste it into here. Okay, so that's the result of looking up rotation. It's in a gazillion places on the internet. This matrix for a rotation by angle theta around a vector x, y, z. So that's the axis. This is how you could. This is one way you could rotate around the Earth. You'll rotate the Earth around its axis. If you know the x, y, z coordinates of the Earth's axis, then there's a rotation that'll rotate directly around that axis. Okay. So this is the most general rotation. Most of the time, we just use rotate x, y, and z. Rotate around x, y, and z. But there's this real generic one here. Okay. So back to over here. Now this should work with these Let's see, which one did I get wrong? Oh, no, I didn't call it translation. I called it, I forgot that I called it translate. See, so I called it translate, not translation. Okay. Okay. So now I'm actually translating it, rotating it, scaling it. See, run it. Okay. See, it got rotated. It's okay. Now it's not very far. Now, what if I push it farther away from the camera? So now push it farther away from the camera. Earthframe View doesn't, let me see if it updates. See, Earthframe View doesn't update. See, I had the image open and it's been updated on the hard drive. And Earthframe View, I wish that's probably the one little thing about Earthframe View that I've noticed that it doesn't do. If this file updates, I don't know if Earthframe View will reopen. There, see, you have to do is there a shortcut? Shift R. See, Earthframe View doesn't automatically update. It should. I think it really should. Most text editors, when you if you have like text pads like that, like here, see, here's what I mean by automatically update. Where's Notepad? Oh, there. Okay, open it with Notepad. So I've got this file open in two places. Save it. I've changed it on the hard drive. See, TextPad's smart. TextPad says, I just noticed that file changed. Do you want me to update it? That's what Earthframe View should do. That would be the better way to handle it. Now I can say no, or I can say yes, and it'll update. Okay. Now notice if I change it here and I save it, guess what Notepad does? What did Notepad do? Remember, the file changed on the hard drive. So is this correct?
No.
Yeah. No. You be careful with your tools. Don't ever use an editor that does what Notepad's doing here. Make sure you use an editor that does what TextPad does. If a file changes on the hard drive, the editor better warn you about that. Notepad won't. This is one of many things Notepad doesn't do right. Okay. This file's out of date, and Notepad does. Now, if you start editing it, things get really screwy. Because now what's in the window doesn't agree with what's on the file, but then it could be that this will just clobber what's in the file. It gets very dangerous. Okay. Don't save. Okay. All right. Now, so Earthframe View doesn't automatically update. I wish it did. That's like the one in all the years of using Earthframe View, the only tiny minor complaint I've ever been able to come up with Earthframe View is it doesn't auto update when a file on the hard drive changes. Okay. Now, I could rotate by different amount. Okay. Then over here, what was it? Shift R, reload. See, there it rotated a little bit. Okay. I could scale it by different amounts. Like here, I'm going to use a non-uniform scaling. I don't want to scale it in the Z direction because it's only got 2 dimensions. So I'm going to scale it by a different amount in the X and Y directions. And go over here and oh, that was a funny coincidence. It ended up being looks kind of, well, it's going to scale to the square turns into a rectangle. When you non-uniformly scale a square, you get a rectangle. Okay. Okay. Now notice how nice this is. See, this is very declarative. I'm saying I want to translate it, rotate it, and scale it. Okay. and I'm not writing complicated loops like we did in the previous render. And what I'm doing here is I'm updating this. Like right now, it's translation by, the matrix here is translation by -2 times a rotation in Z by, say, 55 times a scaling, okay? Okay, so what I'm doing is I'm updating this matrix here, okay? Okay, so and it's in that order. Yeah. Now, here's something funny. What if I change the order? What if I put this rotation here?
Matrices aren't.
Yes,
Commutative?
matrices aren't commutative. Changing the order really matters. Okay, so I'm putting the scaling before the rotation. Okay, now let's see. That won't matter. Some well, yeah, see, it changed it. Yeah, it did change it. So there's one order. Here, let me do the following. There's one order. There's the other order. So this one pushes it back from the camera, and we can comment out this one and comment out that one. So we'll push it away from the camera, then rotate scale. Okay. That gives us that picture. Then change the order. So comment out these two. So this is just a quick way to be able to change the order. Compile, run it. Okay. And now the picture looks different. Okay. So it matters what order you do these things in. Okay. That's going to be one of the difficulties in this. One of the difficulties is the order of operations matters a lot. In matrix, in the world of matrices, M1 times M2 is not equal to M2 times M1. Okay? Matrix, well, when I say not equal to, what does that mean? That means in general. Now, sometimes there are some matrices where M1 times M2 is equal to M2 times M1. There are plenty of examples of specific matrices that do commute, okay? But this is saying in general, you can't make the claim that it's always okay to reverse the order of multiplication. You know, some specific matrices do commute, but most don't, okay? Most don't. So we write as a rule that it's not the case that there's quantifiers here. What we're saying, it's not the case that this is true for all matrices M1 and M2. It is true, there are cases where that's correct. There are cases where M1 times M2 is equal to M2 times M1. And it's sometimes in a linear algebra class, every once in a while, you might be given a homework assignment to figure out what are some examples where two matrices do commute like that. Okay, but in general, it's not. You can't say that it's always true. So we write that equation, but that equation, you have to read it correctly. It should probably be read with the quantifiers, that it's not the case that for all matrices M1 and M2 that M1 times M2 is equal to M2 M1. Okay. Okay. So if you actually wrote it real carefully, you would say this is the long way of saying it. It is not the case that for all M1 and M2, M1 times M2 equals M2 times M1. That's the correct way to say it, but almost nobody ever says it that way. You know, if you look in a linear algebra book, you'll always see it said just this way. Okay, that's the abbreviated way, but not quite accurate way of saying this. Okay, it is not the case that for all matrices M1 and M2, M1 times M2 is the same as M2 times M1. That's abbreviated as M1 times M2 is not equal to M2 times M1. But that's, yeah, you got to be careful. You got to make sure you read that one just the right way. Okay, all right. Now, this is, this is what we're going to be doing from now on. We're building a little tree like this. Oh, let me do one last thing here. Let me give that scene a second position. I think I can do this real quick. Okay, there's one position in the scene. Let's put a second position in the scene. Okay, now, so I'll put a second position. And I'm going to do like we did a little while ago with the, I'm going to give it a matrix. But what I want to do is I want to put a second square, but I want to do like we did before. I want the square I want to put a single square. Put a single square. That didn't draw right. So kind of something like this. Okay, so that position points to that square, and this other position points to the same square. Okay, something like this. Okay, how do we do that? Okay, how can we have the square in two places? Okay, so call this position 1. Call this position 2. Okay, so now there's two positions in the scene. We've created two positions. Okay, this is position 1, position 1, position 1. Okay, and we can make this one. Actually, let's make it easier to read. Make this one position 2, position 2. Make this one position 1, position 1. Okay, and we need to push both position 2. Oh, and I have to do update 2, 1, 1, 1. Okay. Now let's see. Have I got this picture right yet? I have two positions. Both positions are using this same model. See, both positions point to that same model. Okay. There. See, two models. Okay. And I can now move them around. I could move one model around independent of the other. So we've created a little graph already. See, we've created a little graph. Let's see. Let's move one last thing. Let's move one of them off to the right a little bit. So let's move position 1, translate it a little bit to the right. Okay. Okay, so we moved one to the right. Right? This is what we're going to do. This is how we're going to work with, we create a graph. So now we have one square placed 2 places in the scene with 2 different matrices. We've got one matrix here and a different matrix here. Okay, so this matrix puts the square one place, and this matrix puts the same square someplace else in the scene. Okay, and we're using factory methods to build these guys. And this code here, it can be written in a more elegant way too. We'll see a slightly better way to write this. Right now, I'm saying that the matrix in that position should be replaced by this matrix, the product of what's there, the product of what's there now with a new matrix, then replace the matrix. So I'm replacing, each time I do this multiplication, I'm replacing what's in there. Okay, so we should quit there. We run out of time. Okay, so let's see. On Thursday, we'll look more carefully at exactly how the matrices do, like what exactly does a translation matrix look like, a rotation matrix look like, and a scaling matrix look like. We haven't said exactly what they look like. The translation matrix in particular is tricky. That's why matrices have 4 columns, not 3 columns. It's because of translation that our matrices are actually 4 columns, not 3 columns like you'd expect from linear algebra. We're actually working in 4-dimensional space. So all these matrices are actually matrices on 4-dimensional space, not 3-dimensional space. So that's what we'll talk about on Thursday. Okay, so I'll put this little example we wrote up on the course website, and we'll play around with simple examples like this for a while and see like how we write our code to use the new scene structure. Okay, and I'll try to have a new one last program assignment up by I'm working on another program assignment. I hope it'll be up there by Thursday and due at the end of the semester. Okay, so if you have any questions, send me email. Otherwise, we'll meet again on Thursday. Okay. All right. Bye-bye.